Welcome. Today we're going to be talking about the scientific method, how to apply it, how to assess it, what does it entail. Let's start with what it doesn't entail. Scientific method is not a valid way to decipher whether or not we should do something. It cannot help us with moral decisions. It's also not very good at proving the existence of God. It's not concerned with theology. It's not concerned with religion. It's not concerned with the metaphysical, largely. Ironically, the nocebo and the placebo effects are the nemesis of the scientific method in practice. Oftentimes, scientists don't discredit the metaphysical. They don't discredit God. Albert Einstein was known to have said that the more he studies science, the closer he gets with God. Now, what it's largely concerned with is to prove the existence of a phenomenon and look for the cause of said phenomenon as well. So it's looking at, does this exist and what causes this? In nature, the scientific method is progressive. It builds upon study after study after study and closes in on the truth as it becomes more and more specific. In theory, this is what happens. However, if you read the scientific literature, many papers don't adhere to the scientific method, which is extremely problematic. And so building upon papers that don't adhere to the scientific method lead to an absolute misunderstanding of our reality. Largely, the scientific method is concerned with hypothesis testing. It's not concerned with theories or laws. A paper should aim to prove or disprove a hypothesis. In the single paper, it should account for all the variables. A hypothesis should be proven in a single experiment. So I think it's important to understand that scientific method is concerned with hypothesis testing. It should be done in a paper, in an experiment. It should all adhere with itself. We're going to go over the components right now. We're going to talk a little bit about how to assess them in a paper and how they should align in a paper. This is a topic that I will be hounding on for this entire episode. Observation is fundamental to the scientific method. Everything begins with observation, even before the idea stage. Observation was touted incomplete by Abraham Flexner in the Flexner Report there in the early 1900s. And in a way is very problematic because observation is the crux of the scientific method. Everything should adhere back to the original observation. Everything that we're going to talk about should all adhere back to that initial observation. If the results and the observations do not align, or if the interpretation of the results don't align with the observation, then we're not in alignment with the actual nature of things. Of course, with observation comes questioning the genesis of an idea. And it's very important to question everything in science. For some reason now, we shouldn't question this current scientific consensus. We shouldn't question the dogmatic theories that universities push. I know in my university career, I was not valued when I questioned anything. If anything, I was put down by my professors and they attempted to embarrass me in front of the class. And even when the question has a lot of scientific basis behind it, right? That really makes no sense with me. But I digress here. Questioning the observation, what could cause this? What are the potential causes? Does this exist, right? This is kind of in the philosophical state, I suppose. We're really looking at the observation and trying to understand anything we can about it, right? Why does it occur sometimes? Why does it not occur in these scenarios, right? And you're trying to look at different variables, different parameters that you could introduce and include in your experiment. So it's very important to question it. I think spending a lot of time in the observation stage is paramount. Of course, spending a lot of time in the questioning phase is just as important. Spending time in every phase is truly important. The problem now is that we're pushed to create and publish studies as fast as possible. And this does not necessarily adhere to good scientology. It's certainly concerned more with scientistry, which we'll be going over more in the future. But observation is at the basis, and questioning that observation, again, is very, very important. Next, of course, we have hypothesis, the generation of a hypothesis. The hypothesis should, of course, include relevance to the question. The hypothesis should be relevant to the observation. This is where we're really starting to see the alignment. If the scientific question is, do germs cause disease? and the hypothesis is the introduction of a cell culture to a human being, say by injection, you're getting away, one, from the observation, that is contagion being transmissible by just walking by somebody. So you're away from the observation. The question, do germs cause disease? But the hypothesis is the introduction of a culture. Is the culture a pure germ? Is it a purity? Is it isolated? Right? So you need to see alignment within a paper. That's one of the major problems with the germ theory, is that there is no alignment behind the theories, the observations, the results, the methods, and the interpretation at the end. There's no alignment whatsoever. So when generating a hypothesis, it's important to spend a lot of time questioning what the variables could be, because you not only want to talk about that in your scientific paper, what potential co-founding variables there could have been that you have missed, but it's very important to generate a good hypothesis. And we went over hypothesis, how to generate one, how to assess one, the components of a hypothesis in the previous videos. So we'll keep it brief here. The hypothesis needs to contain dependent variables and independent variables. Dependent variables, often noted as X, which I'll mark here. Independent variables are often noted as Y. And so when you're writing your if-then statement, usually you would write something as if Y, then X, right? You could also write if Y occurs, then X occurs. This would be something known as the alternative hypothesis. Of course, you don't always get the results you want, and so there's something known as a null hypothesis, which is very important as well. But if if Y occurs, then X doesn't occur. Oftentimes we confuse the scientific method as being only positive results, but the negative results of scientific method and the scientific literature are just as important. And this is why it's a major problem in the scientific literature that only positive results get published. Only positive results get cited. It's a major problem in citation. It's a citation error, which we've went over in previous videos. But we could draw a lot of conclusions from what science proves to not have any correlation at all, right? Null hypotheses are just as important as alternative ones. Understanding what doesn't cause something is great in the larger picture, right? It's very important within the scientific method and should be in the scientific literature. But of course, there's problems in scientistry where positive literature is promoted and rewarded. And so scientists are only going to publish and aim for positive literature, when negative literature, like negative results or neutral results, are just as important, right? True Scientology would be concerned with that. Now, scientistry is not. It's set up in a way to deviate from the true scientific method. But we're concerned with Scientology here. We're concerned with the true scientific method. And if we adhere to the scientific method properly, it can be useful, right? There are caveats. There are holdbacks to the scientific method, which we'll go over in future videos. I think it's philosophically important to consider, at least. But at the end of the day, a scientific method is a great method when it's used correctly, right? So we need to adhere to the scientific method. We need to create good hypothesis. We need to question the observation, really observe what's going on, create questions, create good hypothesis with good independent variables, with a good valid control. This is a very important part of scientific studies, a control. Something that's not talked about enough is a good valid control. The control needs to make sense within the paper itself. Injecting somebody with a saline solution is not comparable to injecting somebody with a cell culture that is full of microbes and pH indicators, pH stabilizers, buffers, with antimycotics or antibiotics, bovine serum. It's incomparable to a saline solution. So how is a saline solution a valid control for these injection studies? The injections, of course, don't even align with the observation of nature. It should be very easy to induce contagion in another individual. However, all contagion studies have never ever shown any results, but I digress. A good hypothesis is extremely important. The generation of that has to align with the questions at hand, has to align with the research question, has to align with the observation. Creation of a good control, good independent variables, assessing as many independent variables as you can. There should be only, you can test multiple independent variables, right? You can definitely test multiple independent variables, and that's what a lot of studies aim to do, right? And that's important because there are more than one independent variable in nature. Nothing exists in isolation in nature, right? So isolation of the independent variable in itself is something that's very difficult to do. Something that does adhere to the scientific method, though. It can give us information. It can, perhaps, right? But we're going to talk about that more in the future. So next, often there's a prediction made. And this is an interesting part of the scientific method. It's not necessarily something that's going to change the nature of the results or the question at hand, but nevertheless, it's part of the scientific method. Often there's a prediction involved. But more importantly, we'll move on here quickly because that is not something necessarily that you have to assess too much. Next, we're going to move on to testing. Experimentation. Experimentation, of course, is central to the scientific method. Again, I'm going to harp on alignment a little bit here. The experiment needs to reflect the hypothesis. It needs to reflect your initial observations. If your experiment does not have valid controls, if it does not properly isolate independent variables, then it becomes a very unhelpful and uninsightful experiment, right? You're not really testing anything. Of course, in a good experiment, you are going to isolate the independent variables or variable, right? So it's really important when designing a test, if you are to truly adhere to the scientific method, there needs to be valid controls. I'm going to harp on this again, right? This is why the hypothesis is so important, and understanding what a hypothesis is. Understanding the parameters of a good hypothesis, right? More importantly, how does a hypothesis get translated into the testing stage? How does it get translated into the methods of a scientific paper? How does it get tested? How does it get translated into the laboratory? Is the laboratory even a valid way to study something? Does it mimic nature? Does it mimic the initial observation? We don't live in laboratories. We don't live in test tubes. But I digress. The problems in the scientific method. Scientific method is good. It's useful, right? But it needs to be done correctly. The experiment really needs to align with the hypothesis. It really needs to align with this, right? There needs to be valid controls. There could be 10, 20, 50, 100 controls. There should be more controls than experimentation groups, in my opinion. We should be trying to control as many confounding factors as we possibly can to ensure that we're getting to the crux of the truth, that we're ensure that we know what's changing the dependent variable, that we know that this independent variable in our hypothesis is changing, right? We need to be for sure that this is the independent variable, that this is the factor, this is the phenomenon that is creating the change in this other phenomenon. I could go into examples of problems in the experimentation stage. I do want to keep it rather short, but if you're doing a chemical isolation, say you're trying to isolate a vitamin, I think it's really interesting to point out that every step of the way should be controlled. We should be able to control the fact that when you add less lead acetate to an orange to isolate vitamin C, that's the first step, that the addition of the lead acetate doesn't change the nature of the chemical inside the orange. So when we end up with vitamin C, does it actually mimic what's inside the orange? Now this is a major problem. Vitamin C certainly is not ascorbic acid. I'm not sure if we could truly isolate out chemicals that are extremely useful from fruits and vegetables. But I'll leave that at that. That will be a conversation for the future. But I think it's important that this is where we need to control the steps taken, right? There are different ways, there are different studies, there are different ways to do experiments, right? In experiments with people, right? Epidemiological studies, almost impossible to isolate any variables. That's why epidemiological studies should never be taken as conclusions. They should be only used to generate hypotheses. That is the purpose of epidemiology. But far too often we take epidemiology as a fact. Far too often we take epidemiological observation as a fact, when in fact, you've not isolated any variables. You've not controlled hardly anything. So it's very important here, valid controls, there needs to be alignment. I'm going to say that again. There needs to be alignment within your paper. The experiment needs to align with the hypothesis, with the question, and with the initial observation. Injecting people with a concoction of chemicals and germs certainly does not mimic the initial observation of you standing next to somebody in public and the contagion of getting sick, the contagion of infectious diseases. It's not even close. It's not even close to the initial observation. Not that injecting somebody with a pure bacterium or microbe actually provides any results. They need to add adjuvants. They must add adjuvants. If they don't, then they don't get any results, right? An adjuvant is a known ingredient in these injections. It's a known ingredient. It's necessary. These things like aluminum is an adjuvant to stimulate the immune response. So it's necessary. It's a necessary component, but we don't control for it. If we had a control for the adjuvants that we inject into people, we would see that it's more likely that the adjuvant is the substance causing the disease in the first place. And it's interesting because we actually admit that. We admit that the adjuvant is the thing that stimulates the immune response. We admit that the adjuvant is the stimulating factor. It's kind of comical in a way. This is what I was taught in university. This is what is taught in textbooks. This is what is taught in curriculums. This is what is known. However, it doesn't align. It doesn't align with the rest of the studies. It doesn't align with the rest of the scientific method. It's scientistry. It's not scientody, of course. Of course, next we enter the data analysis stage. And this is where triple blind studies are very important. Most studies aren't triple blind, but data analysis, of course, should be objective. You know, you're looking at the results of the study. We talked about this in the past. Objectivity is a must here. It's very easy to lie and manipulate using statistics. Mathematics are great, they're the language of the universe, but statistics can get manipulative. So it's very important to have objective data analysis. Of course, science is not necessarily concerned with objective data analysis. It's even documented in the literature itself, ironically, that, you know, a lot of data is fraudulent or even mistakenly portrayed as a manipulation to show positive results. So that's why you look at raw data. That's why you look at the results section. Even in the results, you can kind of manipulate the way it looks, but numbers are numbers in a way. But when you get into the statistics, it's easier to show something in a certain way. So it's really important that the data analysis is blind and objective. I won't harp on this too much. We talked about this in the past. Of course, there needs to be alignment here with the methods, right? The data should be analyzed in a way. If you're going to present the statistics, I prefer a holistic presentation of statistics. If you're going to present statistics, you should portray it in a very objective manner that portrays them. I prefer to just use as many statistics. If you're going to use statistics, use it all. There's no need to omit things that make it look like results you're not necessarily wanting to get. Anyways, I'll move on from here. From data analysis, of course, we get to the iteration. And the iteration, of course, is very, very important. This is the creation, essentially, of scientific papers nowadays. And within the iteration, right, we're looking at papers. This is when you're reading papers. So you want your words, you want what you're saying to align with everything. You want your words to represent your methods section properly. Does your method section adequately represent what you're saying? If you say we isolated a germ and you show me a cell culture with 10 different chemical ingredients and a bacteria growing in it, well, that's not an isolation, right? So here words matter the most. Here words matter the most. There needs to be alignment, of course, right? And we could get back to the question. The words matter in the question as well. Words matter in the hypothesis, right? But in the iteration, we should really be ensuring that what we're saying in the communication of our study, of the communication of the scientific method into a paper form, to the public, to other professionals, to other scientists. It should be clear, it should be concise. We talked about the iteration. This is scientific style. In the last video, we talked about scientific style. This is very, very important. That's why scientific style is something that's important to assess and address. You know, it's very, very important that we understand good scientific writing, because scientific communication is key. If you can't communicate the scientific method properly, well, then it's useless. It doesn't matter what experiment you've done. You need to be able to communicate it. Far too often, the iteration is misleading and doesn't actually represent what we did in the study. It doesn't represent the method section correctly, right? What they say we isolated a germ when in fact they did not, right? They say we isolated a chemical without actually proving that the chemical exists in the whole food. So this is where you see problems. This is where you see problems, right? Largely, the scientific method is concerned with inductive reasoning. You know, you're going from a very specific hypothesis, a specific question, to try and create a more general interpretation and a general conclusion. Now, obviously, we need to be careful, right? The creation of this general conclusion often leads other scientists on a path forward, right? Often we use deductive reasoning to generate questions and to generate hypotheses, and we actually omit the observation phase. We observe the conclusion of a paper. So in your inductive reasoning, this is a very, very important part. Inductive reasoning is not bad, but if you're going to use the scientific method, it needs to be done correctly to properly reason a conclusion from a very specific premise. And if you're going to use deductive reasoning, you better be damn sure that that's correct, that your conclusion is correct. If you're going to go from a general theory, like everybody draws from the germ theory nowadays, anytime that a set of symptoms comes up that seems infectious, we go, boom, that must be a microbe, a virus, a bacterium, right? So we need to be very, very careful with deductive reasoning. We'll talk about that more in the future. We talked about it on Instagram a little bit. We'll talk about it more in the future. They are useful. They are useful. Just like the scientific method, this is very useful. That's why I'm teaching it. Obviously, we need to know it to be able to assess it. But it is useful when done correctly. But it's often not done correctly. Go read a paper and you know, be diligent and see how much it adheres to the scientific method. New Age studies, right? The neo literature is way worse than the old literature. You know, way worse. You won't even be able to point any of this out. And this is not like I just threw this together. This is the scientific method. You know, I'm scrutinous with, and I'm diligent when I look at this stuff. But you know, it's very important to understand that it needs to be done correctly, because the scientific, this is meaningless if it's not done correctly. If this is not integrated into a scientific study, it's not done correctly, it's meaningless, right? So the scientific method becomes meaningless if it's not done correctly. I like the scientific method. It's fine. It's got its problems, but it's fine. It's a great way to observe and learn and draw causation. But it needs to be done correctly. There needs to be alignment, or else it becomes useless. It's redundant, becomes arbitrary, means nothing, right? That's why most of the scientific literature means nothing, because they don't use the scientific method. Because it's science history. We're concerned with scientology here. Can't wait to make that video. So just for the completion, of course, the iteration is more of an inductive reasoning. The scientific method kind of leading up to this point is inductive. It's going from a specific premise to a more general conclusion. And at the end here, we draw new hypotheses we generate a new question, essentially. You know, and this is deductive in nature. And that can be very problematic. So I just wanted to include that for the completion of the blackboard. But, you know, it's really important to understand these two forms of reasoning. They're not useless, again, right? This is a valid way forward. It should be. This is what science does. But the problem is scientific method doesn't do any of this and then does this and then restarts the process. And then it restarts the process. It skips the observation, of course. We go from the iteration to the question, through the middle section here, to another iteration, to a new hypothesis, and we restart. And the cycle continues, which is why the scientific literature is a house of cards. It is built upon a sand foundation. There's no coherence at all within a study. You know, we're deducing from inconclusive conclusions. We're deducing from methods that don't align with the hypothesis, with the question, with the words in the paper. This is the large problem with the scientific literature. Okay, to conclude, I hope you guys enjoyed that video. The scientific method is not useless. It should be done correctly. There should be alignment and coherence within a study. It can be used properly, and we can deduce from the conclusions so long as the study was done correctly. It's still best to always tie back to observation. Observation is fundamentally the most important part. You know, we can come up with all these assumptions and causations, but if it's not applicable and you can't even see it in nature, you can't even see it in a natural order, then it becomes redundant, becomes useless. Of course, it's very important to understand the scientific method. You can use the scientific method against itself, right? That's what you do to assess the scientific literature. You need to assess the scientific method within a paper. These are very, very important things to understand. So I hope you guys enjoyed it. If you guys like this, found it informative in any way, give us a like, comment, subscribe. You can go down, donate to the cause here. I want to invest more of my time and give you guys higher quality content. So be much appreciated. It's absolutely not necessary. If you did like it, I would appreciate a comment and a like and a subscribe. You know, that's a great way to support me as well. So yeah, this is the scientific method. Learn it, analyze it, practice. Go read papers and see if you can spot any of these and see if there's any coherence within a paper, right? Practice is really, really important when it comes to this. The philosophy and the understanding behind it is part of it, but practicing it and actually learning to assess papers and think for yourself is another level. So that's what I want you guys to do. And we're going to be going over examples in the future. I just want to get the basis out there to you guys. But yeah, begin practicing now, and then by the time we're doing examples, be very helpful. So anyways, hope you guys enjoyed it. Take care.